So, what is the atomic theory? The atomic theory states that all matter is made up of tiny particles called atoms. Each atom is made up of smaller subatomic particles, protons, neutrons, and electrons. The atoms of one element cannot be converted into the atoms of any other element by chemical reaction. Atoms of one element have the same properties, such as average mass and size. These properties are different from the properties of the atoms of any other element. And lastly, atoms of different elements combine in specific proportions to form compounds. The model of the atom has been contributed to by many scientists such as Democritus, Dalton, Thomson, Rutherford, Bohr, and Schrödinger. The first atomic theorist was Democritus, a Greek philosopher who lived in the 5th century BC. Democritus knew that if stone was divided in half, the two halves would have essentially the same properties as the whole. Therefore, he reasoned that if the stone were to be continually cut into smaller and smaller pieces, then at some point there would be a piece which would be so small as to be indivisible. He called these small pieces of matter atomos, the Greek word for indivisible. Democritus theorized that atoms were specific to the material which they composed. In addition, Democritus believed that the atoms differed in size and shape, were in constant motion in a void, and collided with each other, and during these collisions could rebound or stick together. Therefore, changes in matter were a result of dissociation or combinations of the atoms as they moved throughout the void. Although Democritus' theory was remarkable, it was rejected by Aristotle, one of the most influential philosophers of ancient Greece, and the atomic theory was ignored for nearly 2,000 years. The next scientist is Dalton. Dalton was born in Eaglesfield, England on September 6, 1766, to a Quaker family. He had two surviving siblings. Both he and his brother were born colorblind. Dalton's father earned a modest income as a hand-loom weaver. As a child, Dalton longed for formal education, but his family was very poor. After attending a Quaker school in his village in Cumberland, when Dalton was just 12 years old, he started teaching there. When he was 14, he spent a year working as a farmhand, but decided to return to teaching, this time as an assistant at a Quaker boarding school in Kendal. Within 4 years, he was made principal of the school. He remained there until 1793, at which time he became a math and physiology tutor at the New College in Manchester. While at New College, Dalton joined the Manchester Literary and Philosophical Society. Membership granted Dalton access to laboratory facilities. For one of his first research projects, Dalton pursued his avid interest in meteorology. He started keeping daily logs of the weather, paying special attention to details such as wind, velocity, and barometric pressure, a habitat Dalton would continue all his life. Dalton's interest in atmospheric pressure eventually led him to a closer examination of gases. While studying the nature and chemical makeup of the air in the early 1800s, Dalton learned that it was not a chemical solvent as other scientists had believed. Instead, it was a mechanical system composed of small individual particles that used pressure applied by each gas independently. Dalton's experiment on gases led to his discovery that the total pressure of mixtures of gases amounted to the sum of the partial pressure that each individual gas exerted while occupying the same space. In 1803, this scientific principle officially came to be known as Dalton's law of partial pressures. Dalton's law primarily applies to ideal gases rather than real gases, due to the elasticity and low particle volume of molecules in ideal gases. Dalton explained that the repelling forces previously believed to create pressure only act between atoms of the same sort, and that the atoms within a mixture varied in weight and complexity. The principle of Dalton's law can be demonstrated using a simple experiment involving a glass bottle and a large bowl of water. When the bottle is submerged under water, the water it contains is displaced, but the bottle isn't empty. It's filled with the invisible gas hydrogen instead. The amount of pressure exerted by the hydrogen can be identified using a chart that lists the pressure of water vapor at different temperatures. Dalton's fascination with gases gradually led him to formally assert that every form of matter, whether solid, liquid, or gas, was also made up of small individual particles. He referred to the Greek philosopher Democritus of Abdera's more abstract theory of matter, which had centuries ago fallen out of fashion, and borrowed the term atomos, or atoms, to label the particles. In an article he wrote for the Manchester Literary and Physiological Society in 1803, Dalton created the first chart of atomic weights. In a new system of chemical philosophy, Dalton introduced his belief that atoms of different elements could be universally distinguished based on their varying atomic weights. In so doing, he became the first scientist to explain the behavior of atoms in terms of measurement of weight. He also uncovered the fact that atoms couldn't be created or destroyed. Dalton's theory additionally examined the composition of compounds, explaining that the tiny particles, atoms, in a compound were compound atoms. His model was very similar to Dalton's. The next scientist is Thomson. Sir J. Thomson was born on December 18, 1856 in Cheetham Hill, near Manchester. In his early stages of life, his father actually wanted him to become an engineer, but at the time becoming one took a lot of money, and his family didn't meet the needs. Instead, he attended Owens College in Manchester, and later also attended Trinity College, Cambridge, where he became an English physicist. This English physicist contributed to the knowledge of the atom structure with the discovery of electrons in 1897. Thomson had begun testing cathode ray tubes to prove the existence of electrons. These tubes were essentially glass tubes that were sealed and had all the air inside of them vacuumed out. With the tube, a high voltage is applied through two different electrodes, one being the cathode, which is negatively charged, and the other being an anode, which is positively charged. After the high voltage passes through the cathode, a beam of particle becomes present between two electrodes. To test the makeup and properties of the beam, he grabbed two electric plates, one with positive charge and one with negative charge. The beam ended up attracting towards the positive plate and repelling away from the negative one. This concluded that the beam was made up of negative charged particles. He also placed two magnets on either side of the tube and observed to find out that the magnetic field reflected the beam. These experiments helped him conclude that the particles within the cathode ray are negatively charged. Those same particles are approximately 1/2000th the mass of a hydrogen atom, and that these same particles can be found in every single element. Another experiment that Rutherford constructed was the putting model. He had already known that the atom consisted of negatively charged particles. He also knew that the atom had a relatively neutral charge. He claimed that the atom would also need positively charged particles to cancel out with the electrons. These conclusions and that claim allowed him to create the putting model. The model was a depiction of electrons floating around in positively charged matter. Although wrong, his claim paved a way for future scientists to explore and develop his ideas. The next scientist is Niels Henrik Bohr. Niels Henrik Bohr was born on October 7, 1885 in Copenhagen, Denmark. Bohr was the second child of three. His mother was a Jewish banker, while his dad was a professor of physiology at the University of Copenhagen. He received his doctorate degree in 1911 with the dissertation of the electron theory of metals. Bohr's contribution to the atomic theory began in 1912. In 1912, Niels Bohr proposed a theory for the hydrogen atom based on the quantum theory that some physical quantities only take discrete values. Electrons move around a nucleus, but only in prescribed orbits, and if electrons jump to lower energy orbit, the difference is sent out as radiation. Bohr's model explains why atoms only emit light of fixed wavelengths, and later incorporated the theories of light quanta. His model is often called a planetary model because it looks like the sun with electrons revolving around it like planets in their orbits. The orbits correspond to the energy levels, or shells. As the atomic number of the atom increases, the number of electrons orbiting the nucleus also increases. The next scientist is Erwin Schrödinger. Erwin Schrödinger was born on August 12, 1887 in Vienna, Austria. He was an Austrian theoretical physicist who contributed to the wave theory of matter and to other fundamentals of quantum mechanics. Schrödinger entered the University of Vienna in 1906 and obtained his doctorate in 1910, upon which he accepted a research paper at the university's Second Physics Institute. He did military service in World War I and then went to the University of Zurich in 1921, where he remained for the next 6 years. There, in a 6-month period in 1926, at the age of 39, a powerful model of the atom was developed by Erwin Schrödinger. Schrödinger combined the equations for the behavior of waves with the de Broglie equation to generate a mathematical model for the distribution of electrons in an atom. The advantage of this model is that it consists of mathematical equations known as wave functions that satisfy the requirements placed on the behavior of electrons. The Schrödinger model assumes that the electron is a wave and tries to describe the regions in space or orbitals where electrons are most likely to be found. Instead of trying to tell us where the electron is at any time, the Schrödinger model describes the probability that an electron can be found in a given region of space at a given time. This model does not tell us where the electron is, but tells us where it might be. The Bohr model was a one-dimensional model that used one quantum number to describe the distribution of electrons in an atom. The only information that was important was the size of the orbit, which was described by the n quantum number. Schrödinger's model allowed the electrons to occupy three-dimensional spaces. It therefore required three coordinates, or three quantum numbers, to describe the orbitals in which electrons can be found. The three coordinates that come from Schrödinger's wave equations are the principal n, angular L, and the magnetic m quantum numbers. These quantum numbers describe the size, shape, and orientation in space of the orbitals on an atom. So let's recap here. In the 5th century BC, Democritus cut stone till he came up with the idea that if he keep cutting it into rock, it would become indivisible at a point. He called this atomos and went to show his idea to Aristotle, a very influential philosopher of his time, but got rejected. This resulted in his idea being buried for more than 2,000 years. Next comes John Dalton in 1803. Dalton drew up the ancient Greek idea of atomos. His theory stated that atoms are indivisible, those of a given element are identical, and compounds are combinations of different types of atoms. He recognized atoms of a particular element differ from other elements. After John Dalton came J.J. Thomson. Thomson discovered electrons in atoms in 1897, for which he won a Nobel Prize. He subsequently produced the plum pudding model of the atom. It shows the atom as composed of electrons scattered throughout a spherical cloud of positive charge. He recognized electrons as components of electrons, but failed to recognize the nucleus of the atom. After J.J. Thomson came Ernest Rutherford. Rutherford fired positively charged alpha particles at a thin sheet of gold foil. Most passed through the foil with little deflection, but some deflected at large angles. This was only possible if the atom was mostly empty space, with the positive charge concentrated in the center, the nucleus. Rutherford realized positive charges was localized in the nucleus of the atom, but he did not explain why electrons remain in orbit around the nucleus. In 1913, just a couple years after Ernest Rutherford, Bohr modified Rutherford's model of the atom by stating that electrons moved around the nucleus in orbits of fixed sizes and energies. Electron energy in the model was quantized. Electrons could not occupy values of energy between the fixed energy level. He proposed stable electron orbits and explained the emission spectra of some elements. But his model did not work well for heavier atoms. Finally, in 1926 came around Erwin Schrödinger. Schrödinger stated that electrons could not move in set paths around the nucleus, but in waves. It is impossible to know the exact location of the electrons. Instead, we have clouds of probability, called orbitals, in which we are more common likely to find an electron. He showed electrons do not move around the nucleus in orbits, but in clouds where their position is uncertain, and his model is still widely accepted as the most accurate model of the atom. Thank you for watching this very long video, and I hope you have a lot of fun grading it.